Hello, this is Kurt Wallace. I'm a Senior Solutions Engineer at Bright Computing. I have with me Jack Hanna, our Director of Channel Sales, and we're going to talk to you today about Bright Cluster Manager. So our mission statement at Bright is we want to make it easy to install HPC, OpenStack, and Hadoop Linux clusters, and then to manage them over their lifetime. So building a high-performance compute cluster is hard. Most of the management solutions use what's called a toolkit approach. You have whatever your Linux distribution is, plus a collection of tools to monitor and manage and provision and do all the things you need to do to make a compute cluster run. On the screen, there's a list of tools that are out there in the industry. Ganglia, Nagios, Rox, Werewolf, etc. Now, the problem with this toolkit approach is you have to take all these disparate tools, and they have to all be glued together so that they work together. Some of them are easy to learn, but not all of them. Some of them scale very well, but not all of them. Some of them are nice and streamlined, but not many of them. And some of them are designed for HPC, but really not most of them. And if you make a change to any one tool, if you have to update it, then you have to verify that that update doesn't affect anything else in the stack that's trying to manage your cluster. In the case of resources, so each of these tools has their own agent, their own database that the information sits in, and their own user interface to access to do stuff with it. So those are a lot of different piece parts that you have to kind of make all work together. And it takes some work and some expertise and usually a lot of scripting to get this all to work. Right. We took a different approach. So we started and wrote our product from the ground up so that you have a single cluster management daemon, that agent, that provides all the functionality you need. All the data sits in a single database, and then we have a single user interface to access for all your cluster management functionality, which makes our product easier to use, it's more scalable, etc. Now, the way it's set up, so here's a picture of a small cluster. You have your head node on the left and 3 compute nodes on the right. So they're all running the cluster management daemon. A communication between the head nodes and the compute nodes, it's over a SOAP JSON SSL link. Because this is an internal cluster network, these communications aren't encrypted by default. It's a checkbox if they need to be encrypted, depending on what your client's needs are. Now, communication outside the cluster, in this example, to our cluster management GUI, those are using the same SOAP JSON SSL for security. These are encrypted to keep your cluster isolated and secure. And whether you're accessing through the cluster management GUI or the cluster management shell, that's the command line interface. That's all encrypted communication. We also have a web-based user portal, so the end users can see what's going on with their jobs, look at the queues, and do what they need to do. And then we also have an open Python API. So if there are other tools that your customers are using that they want to continue to use, we can integrate with them through that Python API. So the way Bright Cluster Manager is set up, so we have our cluster management daemon, that agent that runs on every node. We secure it with those SOAP JSON SSL for communications. We have X509 certificates for communications between the head nodes and the compute nodes. And then we use an IP tables firewall for external communication. Through that security layer, the cluster management GUI communicates, the web-based user portal communicates, and the cluster management shell. Now, the daemon talks with the operating system. At the moment, we support SUSE Linux, Red Hat Linux, CentOS, and Scientific Linux. In our 8.0 release in April of 2017, we will also support Ubuntu for the customers that need that. So the operating system talks to the hardware. For the most part, our daemon just talks to the operating system. It gets its information there. There are a few things that we talk directly to the hardware for, but we'll talk about those in a moment. So those gray boxes, those are the piece parts that make up the nodes and the other parts of the cluster. And through this communication, we can do all the provisioning. We integrate with workload managers and schedulers. In this green box, that's the ones that we integrate with right now. So PBS Pro, Torp with either MAUI or Moab, the grid engine variants, Slurm, and Platform LSF. So we integrate directly with all those workload managers. We also provide the day-to-day stuff you need to do on your cluster. So monitoring the systems, any automation based on thresholds in your metric alerts. We set up health checks and just the general system management. And included in our distribution is the compilers and libraries and debuggers, et cetera, the things other packages you need to make a cluster run. So here's how we handle provisioning. We use what's called an image-based provisioning mechanism. So when you install the head node, it automatically creates a default image based on the same distribution as the head node. So you have this image, and it just sits in a directory structure on the head node. So the same directories you would expect to see on a Linux installation, you can see right here inside the image. What that means is any changes you need to make to that image, any packages you need to install, anything like that, you can come right into the head node, change root right into that directory, and do whatever you need to do. As you assign an image to a node, we'll send that full image out to that node. We'll send that full image out on the first boot. After that, we can just send the changes, so we can just do a sync install so that you're not bogging down your network. As you assign other nodes into that group, they will get those images and provision themselves out. If you need to make a change, whether you have a change to the core image, or you need a different distribution for a certain application, or for some reason your customers' end users need something different, they can create new images. And those all live on the head node, and then as you assign those into images to nodes, the system will send out those images. And we can work either over an Ethernet or an InfiniBand network for provisioning, whichever the customer wants to use. So as you're creating images, you can either take that default image and clone it and make whatever changes, or you can make changes on a currently running compute node and grab those changes. So you don't have to do it all on the head node, or you don't have to do it all on the compute node. You can do it either way you want. If you need to modify the image, again, the same things you would do to a standard Linux installation. RPM, you can make yum changes, you can change root, you can do all that right in the directory structure. As we're syncing changes, so again, if you make changes on the image on the head node, you can update those changes out to the compute nodes. You can make the change on the compute node and grab those changes back into the head node image. So whichever works best for you. We can work with sending the image out to hard drives on the nodes. If the nodes are diskless, we can use a RAM drive, or we can provision into VMs. And when we're doing the installs, again, as I said, that first install is a full install. But after that, we can just send out the changes. And in fact, if you make a change to an image on the head node, and you want to just sync those changes out, you don't even have to stop the nodes. You can do a live update to the nodes while the jobs are running. So you don't have to bring everything down and reboot everything just to make some changes. We also have the ability to, for larger clusters, if they need to reprovision all the nodes all at once, we can set compute nodes to become provisioning nodes. They will come up, grab the images, start provisioning a set of nodes, and when everybody's provisioned, these nodes will turn themselves back into compute nodes. So you're not wasting hardware for that every once in a while when you reboot the whole cluster. You have access to all the nodes to run compute jobs on. Now our management interface, we've got our cluster manager GUI. It's a standalone desktop application. It's built on the Mozilla framework. So anywhere you can install Firefox, you can install our application. And you can do all your cluster management functionality right through that GUI, and you can even manage multiple clusters out of the same tool. We also have our cluster management shell, the command line. You have all the same GUI functionality, but you also have the ability to do scripting. So all the standard scripting stuff you need to do, looping over objects and all those things, you can do right through the CLI. So here's a screenshot of our GUI. Down on the left-hand side, those are the resources, the parts that make up the cluster, the switches, the networks, etc. You'll notice that we have node 001 highlighted. In the right-hand window, we're on the Tasks tab. So you can see all the things you can do to that specific node. We can power it on, power it off, shut down the operating system, assign it to a specific node so you can group your nodes in different categories to do different things. We can make changes to the software image, whether you want to take the image on the head node and send updates or complete reinstall out to the physical node, or take changes that you've made to the physical node and synchronize that back to the image on the head node, or even grab that entire image back to the head node. And then you've got the other things you would normally do on a physical server. In addition, you can also open up a root shell. So you can open up a console right out of this GUI and do command line direct into that node. The way our monitoring system is set up, so we've got our nodes again, we've got our little cluster. You've got the cluster management daemon running on all the nodes. These daemons, they collect the metrics. Now we're able to do that all in one process, so we don't have separate processes or forked processes to gather all the information. We do it in a single process, so it's very efficient. Then we send that data back to the head node. For Dell servers with an iDRAC, we can also grab information directly off the iDRAC and grab metrics from there. That's one of the times we don't have to interact with the operating system to get information. We can go directly to the hardware. All that information sits in a database. It's not a closed-off database. So if your customers have tools that they want to access this data with, whether it's data analytics or backup or whatever they're trying to do, it's an open database, so they can get to it and get to this data. We also do hourly, daily, weekly, monthly, whatever makes sense for your customer. And we have a database of consolidated data too. And with all this data in the head node, we then form all the graphs and all the monitoring information that you need, and those get sent out to the GUI and the user portal. We interact directly with several workload managers. And what we can do is do automatic installation and configuration. In fact, there's a handful of open source workload managers that we interact with. We can include their software on our distribution, so you don't have to go download it from somewhere else. We already have it on the install. And then we can tie into all their statistics. So all their sampling and analysis, we get all those metrics and have access to them. Now you can either use our GUI, so you have our GUI user portal and command line to access all your workload manager functionality, but we don't lock you into that. If you're already using a workload manager and you like their tools, you can absolutely continue to use their tools. You don't have to use our product. We're not going to lock you out of their tools. It's not going to mess anything up, but we have that option there. We have the ability to enumerate the different GPU resources so that customers can directly, the end users can directly request GPU resources if they have GPU jobs. And that'll also help keep non-GPU jobs from running on GPU resources if there are GPU jobs waiting. If we have a high availability setup with redundant head nodes, we can also automatically configure failover of the workload manager. So if for some reason one of the head nodes goes down or you need to take it down, you fail everything over to the secondary head node and everything will continue to run. We have integrated health checking for our systems. So before a job gets out to a node, we'll run a health check on it. And not only check the hardware, but also check the services that are running. There's a thing called black hole node syndrome where a job will go out to a handful of nodes and one of them won't have a correct service running. And so the job will just stop and it'll never start and it'll kind of evaporate. And it's not easy to see why it didn't start. So we do all that checking before the job gets there to make sure that that doesn't happen. We also have the ability, by tying in the workload manager, we can monitor the workload queues. So as the job queues go down, and maybe you have systems running that aren't running any jobs at the moment, we can start powering those systems down to save you money. And then as the queues go back up, as jobs continue to be submitted, we'll turn those machines back on, provisioning them, and then they'll start taking jobs. So you can dynamically affect your power bill based on your queues. And by tying into the workload managers, we can also do data-aware scheduling to the cloud. So when a cloud instance is running, that's when the meter's running and you're being charged. So we're able to send the data up to the cloud and then gather the results data back down out of the cloud outside the running of that instance. So you don't have an instance sitting there running, charging you money while data is being transferred. For GPU integration, we do a lot of work with NVIDIA. So we have their drivers and CUDA versions automatically in our Bright packages. We can recompile their drivers automatically to make sure that you don't have any driver kernel version mismatch. Again, as I mentioned, we enumerate the GPUs as consumable resources so that users can specifically request them, and you keep non-GPU jobs from running on GPU systems. In addition to our base package, our Bright Cluster Manager, we also have a big data add-on where we set up Hadoop systems. So right on top of a Bright cluster, you can install Hadoop in just a few minutes. We do it out of our own tool, so you don't have to bring in another tool. We work with a couple of different versions of Hadoop, and you can even set up different Hadoop instances on the same cluster. Here's the GUI down in the Hadoop area, so it's pulling back information on the Hadoop stuff that's running. And we do all our configuration through roles. So we have the predefined Hadoop roles, the data node, the job tracker, the yarn server, all the stuff you would expect to see in a Hadoop configuration. We have those already pre-configured, and we can assign and unassign roles just by changing some configuration files and affecting the relevant services. We do have the ability to make what we call a hybrid cluster. So you're running Hadoop and HPC jobs in the same cluster. And we can make it a dynamic hybrid cluster. So if your HPC job queues start to go down and your Hadoop queues are going up, you can take HPC nodes and reassign them as Hadoop nodes, and vice versa. So you're not locked into a certain number of configuration that's variable based on your workload. In addition to the big data package, we also have an OpenStack package. So you can run OpenStack right on top of a Bright cluster. The virtual machines are all managed through OpenStack and then partially through Bright. And we can take the same images that you're using for bare metal hardware and use them in VMs or use them in cloud instances so that you can manage them all the same. So all the typical nodes you have, the roles you have for OpenStack, your Nova for compute, Keystone for identity, Horizon for the dashboard. We have pre-configured roles, and we'll set all that stuff up and then dynamically keep track of the configuration. Again, here's a screenshot of our GUI, looking at the OpenStack and looking at all these virtual nodes. And looking at the whole OpenStack environment, looking at the hypervisor summaries, and other things that are going on in the system. Now in our OpenStack deployment, we use Ceph for all the storage side. We integrate directly with Ceph so we can have it set up and manage it and monitor it. We've also got the S3 and Swift compatible object storage, and then the block storage for the VMs. We also include the Linux bridge driver for Neutron so that you can run this in an InfiniBand environment without a lot of trouble. Two quick case studies. With Cummings engines, we put together a hybrid cluster. So again, they were running HPC and big data jobs on the same hardware, and it was a dynamic cluster. So as their job queues moved back and forth, so did nodes. And this was using Cloudera Hadoop and Intel's Enterprise Edition for Lustre. And then with Saudi Aramco and a regional Dell services partner, we deployed 150 racks, 3,200 nodes of Dell hardware. And these were diskless nodes running over InfiniBand and Gigabit Ethernet, and had it all stood up in less than a day. The 28th largest global supercomputer at the time when it was deployed. And in fact, it installed so quickly that we had time left over to help them enhance their management environment, benchmark the system, and provide them some training. So that's what we do. Again, my name's Kurt Wallace. Here's my contact information. Jack Hanna is our Director of Channel Sales, and our support organization is just support@brightcomputing.com. Thank you for your time.